In this video, we will be doing the last couple of topics of the chapter of circles, which is chapter 9 in the textbook. Okay, we have a few theorems here, so we'll discuss those theorems and then we will do a couple of examples from this chapter. Okay, the first theorem, if you read the statement, it seems quite a lengthy statement, but the idea of the theorem is very simple. Let me explain the theorem directly without reading the statement itself. What the theorem states is that if we have a line segment AB with the two endpoints A and B, and if there are two other points C and D which are on the same side of the line segment, that means in this case both the points C and D are above the line segment. We could have both below the line segment as well. In this case we have it above, but the condition is that the 2 points must be on the same side of the line segment. Okay, and if we have two such points on the same side of the line segment, and if the line segment AB subtends equal angles at both those points, that means if the angle ACB is equal to angle ADC, then what this theorem states is that all these 4 points A, B, C and D will fall on a circle. That means we can draw a circle which passes through all these 4 points. Okay, and that is true when the 2 points C and D lie on the same side of the line segment AB, and the angle subtended by the line segment at both these points is equal. That means angle ACB and angle ADB are both equal, in which case all these 4 points lie on a circle. We call these points as concyclic points. Concyclic points are all the points which lie on the same circle. Let me illustrate this now by drawing a circle which passes through all these 4 points. If these angles are not equal, then we may not be able to draw a circle which passes through all the 4 points. So we see here that we have been able to draw a circle which is passing through all the 4 points A, B, C and D. Okay, so that means these 4 points are said to be concyclic points. So we see here we have C and D are 2 points on the same side of the line segment AB, and as per the theorem, if angle ACB is equal to angle ADB, that is this angle equal to this angle, then the 4 points A, B, C and D, all of them lie on a circle, which is what we have seen here. Okay, if the two angles ACB and ADB are not equal, then all the 4 points will not lie on the circle. So when they lie on the circle, we call them as concyclic points. The next topic in this chapter is what is called as cyclic quadrilaterals. And a quadrilateral is said to be cyclic if all its 4 vertices lie on a circle. So we have a quadrilateral here, quadrilateral ABCD. All the 4 vertices of the quadrilateral are lying on the circle. Such a quadrilateral is said to be a cyclic quadrilateral. Cyclic quadrilaterals have some special property which is stated in this theorem here, theorem 9.10, which gives a property of cyclic quadrilaterals, which states that the sum of the opposite pair of angles in a cyclic quadrilateral is 180 degrees. So that means angle A plus angle C, which are opposite angles, their sum is 180 degrees. Similarly, angle B plus angle D is also going to be 180 degrees because they are opposite pair of angles. So that is a property of cyclic quadrilaterals, and that is the opposite pair of angles add up to being 180 degrees. Okay, the converse of this theorem is theorem 9.11, which states that if the sum of a pair of opposite angles in a quadrilateral is 180 degrees, then that quadrilateral is a cyclic quadrilateral. So if we can show that the opposite pair of angles add up to 180 degrees, then we will say that the quadrilateral is cyclic. In other words, the vertices of the quadrilateral lie on a circle. Okay, we will not be proving these theorems, but you need to remember these properties, which we will apply in solving some problems. Let us now do an example problem for this chapter. So we have this figure given to us here, And in this figure, it is stated that AB is a diameter of the circle. So we have been given that AB is a diameter. The chord CD is equal to the radius of the circle. That means the length of the chord is equal to the radius of the circle. So radius is the line from the center to any point on the circumference of the circle. So CD is given to be equal to the radius of the circle. And it states that AC and BD, these lines, when extended, intersect at the point E. So we are given that AC when extended and BD when extended, they both intersect at the point E, and we have to prove that this angle here, angle AEB, which is this angle over here, we have to prove that this is equal to 60 degrees. Okay, to prove this, we will make some construction in the first place. So what is the construction? First of all, we will join the center of the circle, center is O, with the points with the points C and D. Okay, so from O to C is a radius, and from O to D is also a radius. Okay, so we will draw two radii in this diagram as part of our construction first of all, and then we will take it further from there. Now when we have joined OC and OD, we get this triangle OCD, which is an equilateral triangle because OC is a radius, OD is also a radius, and the chord CD is given in the question to be equal to the radius. So we have all three sides of this triangle to be equal. So that means we have OCD to be a triangle which is an equilateral triangle. And for the equilateral triangle, we know that all the three angles inside the triangle are equal to 60 degrees. So from that, we will get the angle subtended by the chord CD at the center of the circle to be 60 degrees. So we will get this angle here to be equal to 60 degrees. Okay, so when we have joined OC and OD, we get the triangle OCD to be an equilateral triangle, and therefore the angle COD equals 60 degrees. But angle COD is also the angle subtended by the chord CD at the center of the circle, right? Next, we will do another piece of construction where we will join BC. Okay, so once we join BC, we will now have an angle subtended by the chord CD at the circumference of the circle, which will be the angle CBD. So first we will join BC, and then we will see what is the angle subtended by the chord CD at the circumference of the circle. So we have now joined BC, and we need to find out what is the angles CBD, which is this angle over here. What would be this angle? And clearly from the figure, we see that the angle CBD is the angle subtended by the chord CD at the circumference of the circle. And we know that angle COD is the angle subtended by the chord CD at the center of the circle. And we know from an earlier theorem that the angle subtended by a chord at the center is 2 times the angle subtended by the same chord at any other point on the circle. So if the angle at the center is 60 degrees, that means the angle at any other point on the circle must be half of the angle at the center. So that means angle CBD should be equal to 30 degrees. So from this, we have obtained that the angle CBD is equal to 30 degrees. Okay. Now we will look at what is the angle ACB, and then we can find the angle BCE, because ACB and BCE are a linear pair of angles. So first of all, if we can find what is angle ACB, we will then be able to find the angle BCE, and then we can observe the triangle BCE, from which we can calculate the angle E which is desired for us. Now that we know angle CBD is equal to 30 degrees, which is this angle, what is the angle ACB? We can clearly see from the figure that the angle ACB is the angle subtended by the diameter of the circle A, that is the diameter AB of the circle. And we know from an earlier theorem that the angle subtended by the diameter of the circle is equal to 90 degrees. That means angle ACB is 90 degrees. Or in other words, angle ACB is the angle subtended by the semicircle, right? So again, that's our theorem, that the angle subtended by the diameter or by the semicircle is equal to 90 degrees. So we have angle ACB equals 90 degrees. So we now have angle ACB to be 90 degrees. So what is angle BCE, which is this angle here? BCE is also going to be 90 degrees because ACB and BCE are a linear pair. The sum of these two angles is 180 degrees, and since ACB is 90 degrees, BCE will also be 90 degrees. So we have now obtained angle BCE to also be 90 degrees. Now we can observe the triangle BCE, which is this triangle here, from C to E, E to B, and B to C, the blue line. So in this triangle, we know the angle BCE, we know the angle CBE, and the third angle is the missing angle, and we can apply the rule that the sum of the three angles in a triangle is 180 degrees. And since we know two of the angles, we can calculate the third angle, which is the angle CEB, or in other words, the angle AEB. So we can apply the triangle angle summation rule to the triangle BCE. So we now have in triangle BCE, which is this triangle BCE. So in this triangle over here, the sum of the three angles is 180 degrees. So angle BCE plus angle CBE plus angle CEB equals 180 degrees. BCE is this angle here. We know that it is equal to 90 degrees. CBE is this angle here, which is the same as angle CBD. So CBE here is the same as angle CBD. So it is 30 degrees. So we have 30 degrees here. And CEB is the angle E here, which is unknown. So we leave that as it is, and the sum is 180 degrees. And from this, we can now compute what is angle CEB. So we have now obtained the angle CEB to be equal to 60 degrees. But angle CEB is the same as the angle AEB. So therefore, angle AEB is equal to 60 degrees, which is what we have to prove. So angle AEB equals, therefore, angle AEB also equals 60 degrees, which is what we had to prove, and hence it is proved. Let us now do one more example, and we have this figure given here in this example, wherein it is stated that the quadrilateral ABCD is a cyclic quadrilateral. That means all the four vertices are lying on the circle as seen in the figure. And we are given that AC and BD, the blue lines, are the diagonals of this quadrilateral. And we are given angle DBC, which is this angle over here, to be equal to 55 degrees. And the angle BAC, which is this angle here, to be equal to 45 degrees. And we are asked to find what is angle BCD, which is the angle marked over here with the question mark. That is what we have to find. And this is a very simple problem. If you notice that the 55 degree angle is the angle subtended by the chord CD. So we have a chord CD. It is subtending an angle CBD on the circle, which is 55 degrees. And we know that the angle subtended by a chord at any point on the circle is going to be equal. So the angle CBD must be equal to the angle CAD. So CAD, which is over here, which is this angle over here, must be equal to the angle CBD, which is 55 degrees, because CAD and CBD are both angles subtended by the same arc CD, or subtended by the same chord CD as well, right? So either way, angle CAD must be equal to angle CBD. So since angle CAD and angle CBD are the angles subtended by the same arc CD or the same chord CD, both these angles are equal. So we have angle CAD to be equal to angle CBD. And since we know that angle CBD is equal to 55 degrees, so CAD should also be equal to 55 degrees. So we get this angle CAD to be equal to 55 degrees. So once we know what is angle CAD, we can find the total angle A, which is the angle BAD. So we will have angle BAD is equal to angle BAC plus angle CAD, which is 45 degrees plus the 55 degrees, which is equal to 100 degrees. Okay, so we have the total angle A, that is angle A equals 100 degrees. And now we know that the quadrilateral ABCD is a cyclic quadrilateral, and one of the angles here, the total angle A, is equal to 100 degrees. And we know that for cyclic quadrilaterals, the sum of the opposite pair of angles is 180 degrees. So therefore, angle BAD plus angle BCD should be 180 degrees. So we have here 100 degrees, which is BAD plus BCD equals 180 degrees. So therefore, we will have now angle BCD to be equal to 180 minus the 100 degrees, which is equal to 80 degrees, which is what we have to find. So the angle BCD in the figure here, which is this angle over here, that becomes equal to 80 degrees. So the question mark there, that is equal to 80 degrees, which is what we had to find. Okay, we'll stop here and we will continue with the next topics and some more examples from this chapter in the next